Okay, Chapter 6. Section 6.1, Part 2, Slope Fields and Euler's Method. But we're not going to be talking about Euler's Method. Slope fields. We're going to use slope fields to approximate solutions of differential equations and expand that to a few other things for the AP test. Slope fields are really cool looking graphs. Each of these little segments is the slope of the point, of the slope of the graph at that point. And if you try to follow the slope field, you can see that they make different directions. This slope field is written with arrows. So you can see that if you follow that path, it's a straight line, but through different points, it makes different curves and different shapes. This would be like an ellipse kind of shape no matter where you go. These are like ski jumps up and down depending on where you go. This might go up and back down, horizontal asymptote here maybe. So slope fields are different types of graphs based on the slopes at different points. And we know that we find the slopes based on derivatives. So a slope field is a visual representation of all the possible solutions of a differential equation. It's a graph of line segments with slopes given by that differential equation. Our book sometimes calls them direction fields in different places, or you might see that on a standardized test, direction field or slope field. On the AP test, you need to be able to do four things using slope fields. First of all, you need to be able to sketch a slope field from a given differential equation. So if I give you the derivative, you have to find the derivative at various different points and draw the little slopes at each point. Secondly, you might also have to, or you will have to, given a slope field, sketch a solution curve through a given point. And then thirdly, match a slope field to its differential equation. Fourthly, match a slope field to the solution of the differential equation. So let's work on each of those things. To solve a differential equation analytically, it can be difficult or even impossible. However, using this graphical approach called a slope field, you can use that to learn a lot about the solution or the possible many solutions of a differential equation. So if we have a differential equation of the form y prime equals some function with both x and y in it, the function with x and y in it is some expression in x and y. At each point xy in the xy plane, where f is defined, so where you're not dividing by 0, the differential equation determines the slope of the solution at that point. So all they're saying is that if you have some differential equation, like y prime equals 3x over y, you're going to use this equation to find the slope at the point xy by plugging xy in, finding that slope, and then that is the slope of your little tiny line segment. So we're going to draw short line segments with that slope that we found at different points in the domain of f. So that means we're not going to put it at a point where the slope would be undefined. Then these line segments form a slope field, or a direction field. Each line segment has the same slope as the solution curve through that point. So if our curve goes like this, at each point here, we'd have a little tiny slope, little tiny line segment that has the same slope as the whole curve at that point. A slope field shows the general shape of all the solutions and can be helpful in getting a visual perspective of the directions of the solutions of a differential equation. Okay, so example 1, this is the first thing you'll have to be able to do for the AP test. Sketch a slope field for the differential equation. Y prime equals x minus y. We're just going to do these 3 points. So this is x and this is y. So y prime will equal -1 minus 1, which is -2. So the slope at the point -1, 1 is -2. So locate the point -1, 1, and then draw a line segment that has a slope of about -2. -1 would be 45 degrees, so it's steeper than that, so I would say about like that. And it's just approximate. How about the slope at the point 0, 1? So plug in 0 and 1. That equals -1. So the slope at the point 0, 1 is -1. So locate the point 0, 1 and draw a line segment that has a slope of about -1. So that would be 45 degrees. So a little bit less steep than this one. And the point 1, 1, put in a 1, you get a slope of 0. So at the point 1, 1, we're going to have a slope of 0. And you could do that for all the points in this whole grid. The second thing you'll have to do is, here's just another example of the same thing. Sketch the slope field for dy dx equals negative y over x. So pick every point that you want. Here's the point 0, 0. At the point 0, 0, if you plug in x and y, you've got something that's undefined. It's definitely over 0. It's actually indeterminate. So we don't put any point there. You don't draw in slopes for undefined or things that are not in the domain. And anything where x is 0 is not going to be in the domain. So we're not going to have anything here where x equals 0. We won't have any points, little slopes drawn in, any line segments drawn in there at all. But how about the point 1, 0? So if you plug in the point 1, 0, we'll have 0 over 1, so that slope is 0. How about the point 2, 0? Again, any place that y is 0, we're going to have a slope of 0, except here at 0, 0, because x doesn't exist there. So those are all of our values on the x-axis. Then if we choose a point like 1, 1, we have negative 1 over 1. And how about the point 2, 1? We'll have negative 1 over 2. So that's pretty less slanted than this one. How about the point negative 1, 1? Slope of 1. Point 2, negative 2, 1. So negative 1 over negative 2, which is 1/2. So that's going to be less slanted. And you would do that for these up here and these down here, these 4 down here. So if they give you a grid, you have to fill it all in if they don't tell you which particular points to use. The second thing is to be able to sketch a curve through a given point on a slope field. So if I had given you this point, then you would just draw this one curve through that point, just following the slopes around it. Or if I had given you this point, then you just kind of follow through and make sure you hit that point. Oh, I should have went a little bit steeper there. It's just approximate. So how about this one? Looks like we're going to go just kind of follow the way that the slopes are directing you. It doesn't have to be exact. Just kind of follow the way that the slopes are directing you. So it's a sketch, not exact. Example 3 is to be able to match a slope field to its differential equation. So we're going to go to this website. So the okay, so when you get to this website, you can practice with it yourself. I'm going to quiz you on different slope fields and match them. So let's just look at this example. It's negative x over y. How would we know that this is the slope field that goes with the derivatives of negative x over y? Notice that in this first quadrant, all the slopes are positive or negative or changing. Well, let's look at it. They all look like they're negative, except they get pretty vertical here. But in general, they're negative here. Here, they look pretty horizontal. So when they get close to here, they're 0. They get close to 0. And here, they get close to 0 in the denominator. But these are all negatives. So it looks like we have negative slopes here. But here, they're positive. Here they're negative, and here they're positive. So if we didn't know this was the equation, we would think when x and y were the same sign, we end up with negative slopes. So we would know there's a negative on our derivative. Here, when they're different signs, they're positive, so we know that's another verification that there's a negative on the derivative. And then vertical slopes here, horizontal slopes there, so you know that when x is 0, the slope is 0. When y is 0, the slope is vertical or undefined. So it's probably a fraction. And that's how you would check that. So let me give you a couple more. Here. Go to this website, and I'm going to type some in over here where you can't see. And you're just going to be able to see the slope field. think I did this on the next page. Okay, I did. All right, so you can use that website for practice if you want, but let's look at y prime equals 2x. Which of these would make sense to match with y prime equals 2x? So no matter what x is, we're going to multiply x by 2 to get our slope. And notice there's no y in this, so the y value shouldn't matter. So whatever x is, that should matter, and as we go down the graph, the y value shouldn't matter. So the slopes should stay the same all the way throughout of any vertical line. Like if x is 5, all of those slopes should all be the same. They should be 10. That looks like it matches with this one. Here, if you notice, like when x is 5, these slopes change as we go down. So the y value does matter for these. And here, these slopes do change, so the y value matters for these. And here, the slopes do change, so the y value matters for these. So these three, once you plug in a y value, it changes the value of the slope. So they cannot be this first one. So this first one must go with that one. Let's just check a point. Like if we use the point over here, 4, and you put in a 2, 2 times 4 is 8, that could be a positive slope. Maybe this doesn't count up by ones, but as you get higher, as x values get higher, they get steeper. As x values get lower, the slope gets less steep. And at 0, the slope is 0. So 2 times 0 would be 0. So that one does match with that. Okay, we've got to find which one goes with y divided by x, or x times y, or x plus y. The times are sometimes easier because you can just look at the ordered pairs and look at the quadrants and think about the sign, like positive or negative. So if we have x times y and we're in the first quadrant, a positive times a positive would be a positive. So which graphs in the first quadrant have positives? All over. This one does. This one does. This one does. Yeah. Okay, so they all are positive in the first quadrant. How about the second quadrant, where x is negative and y is positive? We should have negative slopes. Are all these negative? Yep. Are all these negative? Nope, here's some positive ones. So we know this can't be the third differential equation, x times y. It's not this one. Are all these positive? Nope, these are negative. So it must be this one, because x times y is positive in the first quadrant, negative in the second quadrant, negative in the third quadrant. Positive in the third quadrant, because a negative x times a negative y would be positive, and negative here because we have a positive x and a negative y. All right. How about y divided by x? We want to look for things like, well, if x is 0, we're going to have vertical tangent lines, vertical little slopes. So vertical lines here, looks like it, and as you get closer, it's looking like it. If y is positive and x is positive, we're going to have positive slopes. Negatives here. Negative divided by positive is negative. Positives again, negatives here. This one probably goes with that one. And then we'll leave this. It must be x plus y. But pick a point. Like, how about this one? If we have a negative x plus a negative y, we'd have a negative slope. Or a positive x and a negative y. We'd have, what is going on here, right? Let's look at that. Or what about right here on this, on all these, on this diagonal here? Notice all these are 0 slopes. Does that make sense with x plus y? If we have a positive x and a negative y and they're the same value, like positive 3, negative 3, that's going to have a 0 slope. Yep, so verify it in as many ways as you can. Fourth thing that you're going to have to do is match a slope field to a solution of the differential equation. So this is a solution. So we have to think about that this represents derivatives, so we better find our derivative. So what's the derivative of cosine? It's negative sine. Or a solution is, what if we drew the curve through any random point? So if I pick a point right here, what would that curve look like? Just follow the curve. Follow the curve. Hey, that kind of looks like cosine, doesn't it? None of these would look like cosine if I drew follow the curve Follow the curve. That doesn't look like cosine. How about this one? Just pick a point, following that curve. They almost look straight, don't they? That doesn't even curve. They kind of all are just straight. So you could either look at the derivatives or just draw the solution curve and see if it goes with what the graph of cosine looks like. Obviously, this is the graph of cosine, right? And this looks like a cube, x cubed. And this looks linear, 3 times x. If you take the derivative and just check it, the derivative is 3 everywhere. So notice all these slopes are exactly the same. They're all a slope of 3. There's nothing that changes in this whole slope field because no matter what x and y are, the slope will always be 3. Here's your homework, and then I have a slope fields packet that I'll give you tomorrow when you come to class, so you could work on those few if you want to get started.